This robot can map a room, navigate autonomously, carry 25 kilograms, and even transport a robotic arm. And you can 3D print almost all of it yourself. Let's build it. We begin with the front wheel module. Press the bearing into the printed housing, flip it over, and add the wheel standoffs. Keep the M8 nuts loose for now. The threaded rods will lock them later. If you're new to robotics, don't let all these parts intimidate you. A capable robot is really just simple mechanical, electrical, and software systems connected together. Build them one by one, and the whole machine starts making sense. Now assemble the middle and rear sections. Slide the battery holder into place, then repeat the process on the mirrored side. Add the bearings and middle pieces, and make sure every captive nut is installed before moving on. What you're building here is the robot's skeleton. It keeps the 4 drive modules aligned while supporting the batteries, electronics, sensors, and whatever payload you decide to add later. Next, the threaded rods connect both sides into one rigid chassis. Watch the lengths carefully. Longer rods go on top, shorter ones underneath. Once everything is positioned, tighten the frame together. Right now, it still looks like printed plastic and hardware, but the next mechanism changes that completely. It's what lets inexpensive stepper motors move a surprisingly heavy robot. Now for one of the most interesting parts, the 3D printed planetary gearbox. Insert the small bearings into the planet gears, secure them with the bolts, and arrange the planets around the sun gear. Add the final planet, then gently flex the ring gear so the assembly can slide inside. Finish with the rear bearing and bevel gear. If you've only seen planetary gearboxes in diagrams, building one makes the idea much easier to understand. The motor wants to spin fast, while the gearbox trades some speed for much more usable torque. That's how affordable NEMA stepper motors can move this platform quickly while carrying around 25 kilograms. And because you printed the transmission yourself, nothing is hidden. You can inspect every gear, change the reduction, redesign a part, print another version, and see how your changes affect the robot. With the gearbox finished, install the NEMA 23 motor and its mount. The sun gear locks onto the motor shaft from above. Now the motor, planetary reduction, bevel transmission, and output form a drivetrain ready to turn power into wheel torque. Now finish the output side with the bearing, bevel gear, standoffs, and wheel shaft. Make sure the M5 threaded rods sit correctly and tighten the set screws firmly. If this connection slips, the motor can spin while the wheel does nothing. If the bevel gears resist, rotate the shaft with pliers until the screws line up. The other drive modules work the same way. Building teaches you more than watching. You can trace power from the motor through the gearbox and bevel gears all the way to the wheel. With the mechanical muscle finish, we can add power, sensors, vision, and autonomous navigation. For power, I'm using cordless drill batteries because they're strong, removable, and easy to find. But you can adapt the robot to a suitable, 12 or 24 volt battery you already have. The side mounts also hold smartphones, turning old phones into useful cameras and sensing devices. Now the electronics go in. Mount the ESP32, install the DC converter, and adjust its output to 5 volts with a multimeter. This is where the platform starts becoming a real robot. It already supports SLAM and AI navigation, so it can build a map, estimate its position, and move through an environment without following a fixed path. Add cameras and distance sensors, and you have an affordable platform for learning the same ideas used in warehouse, delivery, and research robots. Now close the body around the electronics. These panels carry the ultrasonic sensors and LED strips, so the shell is also part of the sensing system. Secure everything with standard M3 bolts and continue around the chassis. The best part is that nothing has to stay exactly as I designed it. Add another sensor, mount a Raspberry Pi or Jetson, redesign a panel, or print a new one. That's when you stop following instructions and start turning the robot into your own platform. Install the remaining LEDs, the main power switch, and the female DC connector. That connector is here because this platform can carry a robotic arm on top. So the same robot can become a warehouse AGV, an autonomous delivery platform, a SLAM research robot, or a mobile manipulator. Imagine sending it somewhere autonomously and then using the arm to pick up or interact with an object. You can start with simple driving today and keep adding capability as your skills grow. The remaining shell pieces mirror the side we've already completed, so there's no need to repeat every bolt. This is where the build becomes satisfying. A few minutes ago, it was bearings, threaded rods, printed gears, motors, and loose wires. Now it actually looks like a robot. And this isn't just a CAD model. Makers around the world have already built and tested this design. Start with something proven, learn how it works, change one thing, break something, fix it, and keep going. That's how you move from copying a project to engineering your own. These are the omnidirectional wheels. Join the halves with M3 bolts, insert the rollers, then mount the wheels onto the shafts. Add washers, tighten M5 nuts, and the mechanical build is complete. If you want to build one, the description has a bill of materials, print files, wiring instructions, programming software, SLAM and AI navigation software, and the software used to create this assembly manual. The robot kit is also coming soon. Don't wait until you understand everything. Print the first part, build something, and learn robotics by actually doing it. Let me know in the comments, what would you use this robot for? Thanks for watching, and see you in the next one.